morning. Okay, so for today's attendance question, let's try the spherical coordinate. The question says, well, as you know, what kind of coordinate system we're using depending on what kind of integration region it is. Now, this question says we have a integration region that's a solid ball. We want to find the volume of the part of the solid ball that has radius less than or equal to 1. So that's within the solid ball of radius 1. So that's radius is below or equal to 1. That's for any point within the solid ball. The cone is, so we're not finding the volume of the entire ball. We're finding the volume of a certain part of the ball. Even when all the way using phi as notation, if you remember, in spherical coordinate, phi representing angle between the z-axis. So we have this is a z-axis. Okay. So the first angle is phi pi over 3. So from here to here, this angle is pi over 3. On the other hand, the other angle is 2 pi over 3. So it's all the way from here to here. That is 2 pi over 3. So we're saying between these two angles, that's the volume we're calculating. So if we try to like color the part of the volume of this, then something that is right, kind of like this. So we're only finding part of the ball. So then there's a cap at the top and the bottom part and top part. Not calculating. So maybe it's easier if we look at this recording to understand spherical coordinate better. But let me make sure if you attend online, the sum will be some share. Sure, if you if some will be canceled. Sometime only the voice outside the computer will be recorded. So I'm not sure if I show the recording. What's in the computer will be displayed. Okay, now it's the speaker and then I'm not sure if I show the recording, you'll be able to hear it online. So let's try it. I'm not sure. Sometimes people complain that when students attend online, the computer voice is not. Even if you cannot hear, if you're online, you're on the computer, so you can actually run this video on your own computer. So that way you can hear the recording. So I'm just trying to see a better visual with this recording to explain it. Okay, I think this video explained the fee, especially the fee, a lot better than what I can do. The visual is really nice, so if you want to look at more example, you can finish the video. But for our question, I think I can see that I can understand how fee works in here. So basically, this is a pi over 3, and then the larger one, the 2 pi over 3, went all the way down. Then this is a cone that has a 3 pi over 2 pi over 3. The top cone has the pi over 3. And then therefore the top part and the bottom part are not belong to the volume that we calculate. So anyway, now in here, for this question that we want to calculate, the pi over 3 and 2 pi over 3 will be the integration limit for phi. And when you are calculating the volume, and based on what we mentioned before, a volume calculation is a triple integral of a differential of, this is a differential of the volume, so this is a three-dimensional differential. So the dv should be calculated by like dx, dy, dz, but we're looking at dv in a spherical coordinate. This is something I mentioned earlier. dv in spherical coordinate, dv equal to rho square sine v theta dc. So following that idea, in order to do our calculation, we'll be doing a triple integral of. So here you have to write out how you want to interpret the dv for your volume calculation. So it should be sine more visible. Into like rho square sine v, right? And then d rho dv dc. This is our spherical coordinate integration variable. So our integration variable, only the rho is a distance, the phi and theta are angle. So we need to determine their proper integration limit. As you can see, we still have a full rotation to the theta, which is, this is our x-axis. Axis go all the way around the z-axis. So the x value, the theta is from 0 to 2 pi. The integration limit for theta. And integration limit for phi, we have that limitation there. Phi is from pi over 3 to 2 pi over 3. Integration limit for rho, we have rho less than 1. So rho also has to be natural bigger than 0. So 0 to 1 is the integration limit. So this is pretty much how we set up the entire integration. I hope that you can finish the calculation to see how the answer about. Okay, so let's finish the calculation. I hope it works out. If you have already finished the calculation, I can start the scanner so you can receive solutions.
Okay. I was just gonna say, like,
Okay, you need that page.
yeah, I was just gonna look at the calculation,
Okay.
so.
All right, so if we integrate one by one, by the iterated integral, we integrate rho first. So with the rho, we have a rho square. So integration rho square d rho, you would have rho cube over 3. Also have to put in the integration limit d1 that will give you a 1/3. So that's what we have after we finish integrating the rho. And then we can separate the variables. This is a single number, so we worry about having variable limit, all the integration limit are numbers, so which made it possible for us to separate the variables. So the second layer of integration is pi over 3 and 3 pi over 3 for dphi. So we finish integrating dphi, we're getting 2 pi over 3, right? It's 2 pi over 3 minus 1 over 3. For dphi, we're getting pi over 3. For the roll, we get 1 over 3. And then for d theta, there's no other relation that's tied with theta. So theta is a free variable. 0 to 2 pi d theta, we get 2 pi. That was weird. I think I finished. I did wrong with the d phi. Try to correct myself. D phi, there's a sine phi. I forget to integrate that versus this is not good. The d phi should be sine phi d phi. I thought it was 1 d phi. I was totally over sine phi. Okay, so let's get rid of this one since it's incorrect. So we finish integrating rho to get 1/3, finish integrating theta to get 2 pi, and finish integrating sine phi d phi, we get negative cosine phi. Put the antiderivative, put in the integration, then 2 pi over 3, and pi over 3 would be getting. So let's multiply 1/3 with 2 pi, we'll get 2 pi over 3. Then for negative cosine phi is negative cosine 2 pi over 3 minus negative cosine. Minus negative means plus cosine pi over 3. Yes.
I was gonna say like pi over, like the cosine of pi over 3 would probably be 1/2.
Right, okay. So cosine over 3 is 1/2. That means this is 1/2. And that will be negative 1/2, negative 1/2, negative, positive. So it's 1/2 plus 1/2. And here we have 2 pi over 3. That's when everything is finished. We probably should know the answer. Okay. So let's check our work. I think most of us should already have the right answer. If you didn't make the same mistake I made, sorry, we get the sine phi. Make it. Oh, you go all calculation. This is what we did. Okay, thank you. So
Hold on, Ed.
what if you all have the link? Because I think I'm missing one person. We have 8 students online, 5 in person. So we should have 13, but I only received 12 answers. Anyone needs more time? One of us didn't submit. If you need your link, let me know if you're online. Those answers not submitted yet. So let me know. I can see most people's name in Teams app, but I think I'm not sure if you don't put your full name and verify your attendance. Right, this is today's attendance question. Okay, let me turn this on so you can submit your answer. Okay, so I guess now I know who it is. Right, so the answer is D. And then you can see this is a calculation. This is a simple example where the integration limit for all 3 variables are numbers. Do you have any homework question you want to talk about before we finish 13.7? Any homework question? Okay, so let's continue. Yesterday we were going over the 13.7, looking at how do we change integration variable when the integration region require a circular region, a cylindrical region, or a spherical region. So we went through a few examples on cylindrical integration region. So now we're moving on to spherical integration region. That's when you have a sphere as your integration region, or when the definition of the integration region involve x squared plus y squared plus z squared, that's when we would know that the integration region is actually a spherical. So these are a couple of equations that will make it possible for us to do the substitution of variable easier, because we need to change the variable, which including the integration function, integration variable, and also integration limit. So these are a couple of things we might want to pay attention to. And you can see the cosine phi, because phi represents angle between the z-axis and the ray that connecting a random point to the origin. So z value divided by rho is cosine phi. I think I went through this yesterday also. And we can see that the z is equal to rho cosine phi. The equal to rho cosine b, therefore cosine b the over rho. Also x squared plus y squared plus c squared equal to rho. So if the over rho, then the root of x squared plus c squared. Also the tangent theta means that we take these two equation for y divided by equation for x will give you tangent theta. That's one of the major relation allows you to substitute for theta. Yeah, so these are a couple of information that might be substitution variable. So let's look at some question for how do we convert the coordinate system. Suppose we have a spherical coordinate, which means the first coordinate is a distance, the second and third coordinate are angles. How do we find their Cartesian coordinates, which means we're trying to find their x value, y value, and z value. Now, based on formula x equal to rho sine phi, remember rho sine phi is a r in the xy coordinate system. This essential x equal to r cosine theta. R is rho sine phi. You plug in the phi and plug in the theta and plug in the rho, which allows you to calculate the x value. Similarly, y equal to rho sine phi sine theta, and then we enter all three numbers to calculate y value. Z equal to rho times cosine phi, following the formula of the spherical coordinate change, we're able to calculate. So from a spherical coordinate to a rectangular coordinate, you follow the equation that we see here, the x formula, y formula, and z formula. Now, let's see how the spherical coordinate can be applied to solve the problem. This is one of the questions that we've done before in 13.3 when we're talking about polar coordinate for the volume calculation. We went through this example. We proved that the volume for a sphere is 4 pi r squared divided by 4 pi r cubed divided by 3. So we're proving that one more time with a much easier method. If you remember last time when we were doing the polar coordinate, we have to identify upper boundary and lower boundary for the z value, which we will get z equal to r squared minus x squared minus y squared. So then z equal to positive r squared minus x squared minus y squared divided by minus the negative. The lower limit for z is negative r squared minus x squared minus y squared. So the calculation is a little bit more involved in that part, and that's also bring out the reason that polar coordinate will be necessary since we have x squared and y squared summation in that calculation. All right, so here with spherical coordinate, we could make this a lot easier. All we have to do is the radius is the rho is from 0 to r. Theta is 0 to 2 pi, and phi is from 0 to pi. This is all the standard integration limit that we see in the spherical coordinate. We're having a full sphere there. And then the integration, when we change the variable, the dv becomes square sine phi will be phi d theta, with all the integration limits set up, and how to finish integration of the d rule and sine phi dt. This calculation kind of finished similar. It's a simple sphere. What we were calculating in the bigger question is part of the sphere. So all there's different is we have the integration limit for the phi. So this is our pi over c for lower limit to pi over c for the upper limit. If there's any difference between this example and this example. So this example we have the phi would go from 0 to pi. Phi the maximum value for phi is 0. Minimum value for phi is 0. Maximum is at pi. So the antiderivative is negative cosine phi. We put in 0 pi to get that calculation that gives us 2. Right. Unlike earlier, we would have it was 1 actually. So so if you think about it, this is actually half of the whole sphere. There's a 2 pi over 3. But here we have the full sphere, which is why we have 4 pi over 3 in here. So the practice question on the clicker kind of echo what we have in this example. It shows a much quicker way to identify volume of the sphere. And this kind of reaffirms the formula again. 4 pi over 3 times r cubed. Volume is 3-dimensional measure, so the distance measure is being cubed. Plus the coefficient. The pi there is because you have a circular or spherical integration region. Whenever there's a circle involved, you always see pi as a coefficient. All right. The second question is to calculate this integration. We're integrating x squared plus y squared plus z squared dv. Okay. Again, the integration function is not the one determining the type of integration that we were supposed to do. Integration region is, in this question, integration region is d is a solid that lies above the cone d equal to root of x squared plus y squared, but below the sphere of radius 1/2, center at 0, 0, 1/2. So if we want to set up the proper integration calculation for it, and you see the formula, so it's very clear which function we're integrating, but it's not so clear about the integration region. So we would, best way will be try to visualize what was the integration region. The cone is equal to x squared plus y squared, which will be, this is the cone that we're drawing. The sphere is a ball, but this is the sphere center at 0, 0, 1/2. So I draw a sphere over here. And then you can see the sphere will be intersecting the cone, and then it says here lies above the cone, but below the sphere, like a cone that has a round top. Think about ice cream, and that was the box. That was the integration region there. Okay, so now we're gonna try to identify what will be the integration boundary for phi, for rho, phi, and theta. Okay, and number one is we are trying to change the integration variable. The x squared plus y squared plus z squared, we mentioned that before. In spherical coordinate, using this formula, rho squared equal to rho squared equal to x squared plus y squared plus z squared. So that's why I write rho squared, the green one, for the integration function. But then there's a dv. We are turning the differential notation dv into an actual integration variable. It equal to, since we're doing spherical coordinate, dv equal rho squared sine phi d rho dv theta. So make sure nothing is missing. Make sure when you are converting from a symbolic notation at the question to an actual question that we can follow. So we write out the function that we were supposed to integrate and write out the variable layout. And now let's identify the integration limit. Number one, about the relation between the x-axis and the axis, we're rotating the whole thing, the whole full circle around the z-axis. So the number one thing we know the integration limit for theta is 0 to 2 pi. All right, and I'm gonna try to identify integration limit for rho and phi. That you have to exactly know how it's project onto the xy axis, which is formed by the RD x equal to r cosine theta, y equal to r sine theta. So we're projecting this out to the xy plane, so I can see what would be the natural boundary. So I'm pairing these two equations together. D equal to root of x squared plus y squared is d in our equation is equal to our rho cosine phi over that's fair enough. Let me try to pop this over to try to explain the reason. I think I try to draw that not line in class. So the first equation is from this equation, because the x is here. This is the phi. This is the z, and we draw from this way. This is perpendicular. That was a rho. Okay. So this part is projected onto the xy plane. That was the r. Okay. So this part is a z. So cosine phi is adjacent over hypotenuse. So cosine phi is z over rho. Okay, so then we naturally have a z equal to rho cosine phi. I'm trying to write that rho. That's the z equal to rho cosine phi. On the other side, we have root of x squared plus y squared, which equal to r, which equal to the r. Is the r in the xy plane? But in the xy plane, x squared plus y squared equal to r squared. But if we project it here, it's this part. This is the r. Okay, so this r is actually the sine phi. That was this r. Sine phi equal to opposite, which is r over rho. So the r actually equal to rho sine phi, which also equal to x plus y squared. So this basically become this. Okay, and which actually indicating that rho, it's indicating the angle of the cone. Basically saying you cancel the rho and you have cosine phi equal to sine phi, which then equal to tangent phi equal to 1, which means phi equal to 3. So this angle here is 45 degrees. Okay. So that's relation of the cone is a 45-degree cone. 45 degree is the angle between the side of the cone and the axis. 45 degrees. That was actually, so it looks like the opening is around 0 all the way to 45. It's providing the boundary for phi. 0 to pi over 4. That is the integration region for phi. A little bit more visible there. Okay, and then following that, the other integration limit is this. I'm trying to write that into spherical coordinate. The original equation is a rectangular coordinate, center at here with radius 1/2. So writing that the distance between the origin and the edge is root of x squared plus y squared. That was a 0, and x minus 0, x y minus 0 square, and then z minus z squared equal to 1/2 square. So writing the equation of the sphere with a given center. All right, and then now the equation in rectangular coordinate, I have to write it into a polar coordinate. X squared plus y squared plus z squared equal to the rho squared. And there's a minus z in here, and there's a plus 1/4 there. So rho squared minus z, there's this 1/4 cancel that 1/4. That's what we have. And z equal to rho, v equal to rho times cosine phi. And then obviously we have rho equal to 0 and rho equal to cosine phi. So that ended up being this sphere had a formula rho equal cosine phi. So it was really long equation in rectangular corner, but it was really short in the spherical. Rho equal cosine phi represent that sphere. This is going to be the upper boundary for rho. So rho has the upper boundary of cosine theta, lower boundary of 0. So I hope that kind of explained what was the setup here. So this is after I messed it up in the when I was writing over things. So hopefully this will explain the upper limit integration limit for phi, which is pi over 4. an upper limit integration limit for rho, which will be the edge of the edge of the sphere. Okay, so the power 4 obviously handle the cone, and then the rho equal to cosine v handles the equation of the sphere, kind of bounded the whole thing in spherical coordinate. Once we have the whole equation set up, then we have now the integration limit for all 3 variables, and the rest is a calculation. So this is a textbook solution. I'm trying to explain why it comes natural for those integration limit. And the integration part of it, we integration rho for rho to the power 4 be rho. We'll have rho to the power 5 over 5. Put in the integration limit, we'll have cosine phi to the power 5 over 5. And then we bring the 5 to the outside. And then cosine fifth power phi times sine phi d phi as the nth derivative of cosine power 6 phi. See, we can do a substitution of variable u equal to cosine phi, then du would be negative, right? Derivative of cosine is negative sine phi d phi. So that's why we have this negative there. So the antiderivative of u to the power 5 is u to the 6 over 6. That's what we have. After writing back to the original variable, put in power 4. That will be the answer here. Everything behind the rest of the integration is not too hard to see the process. Any question? So I hope that kind of explained the set of integration limit for that. Right, so these are all the examples that we see in this section. The homework for 13.7 has already been assigned. I also changed all the other dates, so they all due on November 6th, because supposedly, I hope, we're finishing 13.7, which is the last section for chapter 13. You can see chapter 13 pretty much is all about integration method. There's double integral and there's triple integral, multivariable integration. So we're ready for, if we finish the homework for chapter 13, we're ready for the test. This will be test 4 now. So for the time being, I set the test 4 date to be next Thursday, which will be November 6th. So if the test 4 it would be on November 6th, then maybe I should set all the homework are due on the same day. Hopefully by then we should finish all the homework and we should be ready for the test. Any question, concerns? Do you think we'll be able to finish all the homework by then? Again, the practice question for test 4 is already online. Got it under overview, 2, 3, and then that's test 4. This is a study guide for test 4. We have the double integral on triangle integration region, which belong to one of the homework on 13.1. The volume calculation under a surface under 2-meter question. That's one of the question on 13.2. Full coordinate calculation from 13.3. You see, we're pretty much getting one question per section. Total mass and central line calculation. This is a one. Even I made mistakes, so I understand that is the one that is more time consuming, more likely to make mistakes. So please finish your homework on this. And we don't have a lot of questions on this, but we should be able to practice more to get to like lower the likelihood of having error. I understand all human beings make mistakes, but if your steps are clear and your writing is better than mine, then it's easy to follow. It's less likely to make mistakes. And also I can give, you can earn most of the credit for knowing the right method. Right, 13.5 on the surface area calculation, 13.6 for triple integral, 13.7 is triple integration with spherical coordinate. And then there's one more question from 13.2. It was the average value calculation. I was like single out of 13.2. It's kind of interesting to see how a multivariable function's average value can be calculated using integration as a method. that's the plan for test 4. You can try a version of the test 4 and put a practice set is over here. This is all a copy of the practice set. The actual questions are not going to be identical to it, but it should be something similar to it. And you can look up the solution. I think it was a handwritten solution again and write it out. Because I can write better if I have better device. When I write on computer, it was awful, but the good part is it's very visible when it's recorded on the computer. I tried other method. I tried to record the whiteboard in the classroom. It was really hard to read. So I felt like maybe even though it was awkward, at least it's very, very visible. Okay, so that was the plan. Any concern, comment? All right. The final will be covering chapter 14, but so cumulative. The final will be cumulative. It does have some questions from chapter 14. So the final exam should have more questions than the regular test. A regular test, we have 8 questions. I think probably would be 15, at least double the size. So a few of those questions are going to be from chapter 14. My plan will be having 1 question per section. Chapter 14 has 5 sections, so there will be 5 questions from chapter 14. And then the rest of the question is from the other sections earlier than chapter 14. So we're not going to have a individual test over 14 because I don't want to have 2 exams by the end of the semester. So the end of the semester, we have a final exam. We do not have 1 more structured test. So, any other questions? Any other questions about test 4 or homework? Okay, so let's look at the question from 13.7 on the webboard so we can practice with you more variety of questions. Every time I work out a question on the spot, I'm like waiting for the mistake to happen. All right, so let's see. This is question number 1. Right, as you read 13.7 focus on spherical coordinate or cylindrical coordinate, which one do we apply depending on the integration region. This question is to try to find the volume of solid that lies within the sphere. This looks like a radius 5. This is 25, root of 25 is 5. So radius 5 sphere above the xy plane and outside the cone of z equal to 8 root of x squared plus y squared. So you see z equal to root of x squared plus y squared is a cone that we mentioned earlier. That is a cone that has 45-degree angle. So then the coefficient will be indicating, if you remember, will be indicating elements of graph. If we want graph multivariation. Okay, just want to illustrate how it looks like. V equals square root of x squared plus y squared. Okay, so that was 40 degree. You see that this angle, that was 45 degree there. Now, if we change that, like the whiteboard question. It was 8. So if we multiply by 8, 8 times, it looks like this. So what happened is the tangent of the theta become z over z. This is the z. Root of x squared plus y squared is this. So so z over this is cotangent. So the cotangent is 8. The tangent of the z is this over z. So the tangent is 1 over 8. That's why it's the angle is so small, because it's a small tangent value. All right. Anyway, mention that just so we can understand the figure. So let's try to copy this and see how we do the first question. Right. For 13.7, there is already a copy of solution Georgia view under the home solution. I want to work out one question in class so you can see the process. If you look at 13.7 solution. So if you want to know individual question how they worked out, there's a version of the solution there. Let's try to develop the solution from the beginning. So here we have now this sphere we represented by rho equal to 5. Okay, so what it looked like is going like this. We have a cone. This cone, a really tall cone. And then we have a sphere. So the sphere will be intersecting the cone at a edge. Okay. So what happened is within the sphere, but about the cone. So we're trying to find the region inside this. So that was the volume that we're calculating. So it kind of like an ice cream cone with a round top. The round top belongs to this surface, right? And the edge of the cone, that's the ice cone, the ice cream cone peel. This is represented by this. So when you try to set up your volume calculation, it will be like this. Okay. When we try to identify the integration boundary, you need to write a representation of the dV will be rho square sine v. So that would be our integration function. And we've been doing this several times now, kind of see. Then we have d rho dv d theta. Again, this is a full circle as far as the theta goes. Theta's relation is the x-axis. So this is going from 0 to 2 pi on the theta. Okay. For the rho, we have rho equal to 5 being the upper limit for rho. So rho is 5, 0 to 5. And then what about v? You can see it was the axis here. And c goes all the way this way to this angle. So the smallest angle for v is 0. The highest one, see, it's gonna rooted by that. And then you can see it was this was r and this was v, and this is a v. So that was the root of x squared plus y squared. This was z. So we have a tangent of the v that equal to 1/8. I wonder if that made it easy for us to remember, but or you can think of the reasoning like this: z equal rho times sine v cosine v. Z equal to rho times cosine v in the spherical equation. And then this one is 8 times sine v, 8 times rho sine v. This is rho sine v. That was a radius r equal rho sine v. Rho sine v. Okay, divide both sides by rho, most of the part, rho is down 0. Divide by rho, then you have the tangent of v equal 1/8. So anyway, I'm trying to get to this equation so that we can have the upper limit of the angle. We'll have an upper limit that is arctan or tangent inverse of 1/8. That goes in here. So the upper limit here should be tangent inverse of 1/8. That goes right there. So that's the integration limit for all three variables. Now we're going to finish the integration. It's very similar to what you see in the paper question or in the question online. The antiderivative for rho squared, the rho is rho cubed over 3. And we're integrating it from 0 to 5. So we have 0 to 5. So this antiderivative is going to be 5 cubed over 3. Right, that was the rule. And then the d theta, we have the d phi, this sine phi, d phi will have negative cosine phi. Then we have upper limit. Lower limit is 0, upper limit is tangent inverse of 1 over 8. So it's a little weird. So it would be negative cosine of tangent inverse 1 over 8 for the upper limit. Lower limit is minus negative cosine 0. Cosine 0 is 1, so plus 1. So that's the base. And then last thing was d theta, 0 to 2 pi d theta give us 2. So have this number times this number, so that would be the full answer. This will finish the whole question. How awful it looks like. That's a full calculation. So we're gonna put in the answer on Webword just to double check the work. Okay. So 5 to the power 3 over 3 for DC. And then it was 1 minus arctan tangent inverse of 1 over 8. So that was for DC. And then we multiply by 2 pi. That's for d theta. So this question we can separate the integration variable. So I forget the cosine. Cosine. Cosine of arctan. I don't know what was a mistake then. Integration 0 to 5. The volume and the solid. Outside the cone. Okay, so the integration rate, I should read the question more careful. It says lines within the sphere, but above the xy plane and outside the cone. Not inside the cone, outside the cone. So we are doing this instead. Outside the cone. So what I calculated was actually inside the cone. Outside the cone. All right, since I already did the calculation, I don't want to redo it. Since I calculate what's the volume inside the cone, all we have to do is take the volume of the whole sphere. It's inside the sphere and outside the cone. So we do a subtraction. So we would, the whole sphere is 4 over 3 pi r squared. The r is 5 times 5 cubed. So this is volume for the whole sphere. If you subtract the volume within the cone, you should get the volume outside the cone. It also says about the xy plane. So let's subtract. It's half of the sphere, so 2 over 3 and subtract. Right, so I guess I fix it by a subtraction. Upper half of the sphere, half of the, it's above the xy plane. So we're not supposed to calculate, we only calculate this part. We try to plot it so it'd be easier to differentiate. Yeah, so we're calculating outside, above the xy plane, outside the cones. That's the part. So we take half of the sphere minus the volume that I calculated within the cone. Another way is actually find out appropriate integration boundary. So what should we fix? It's outside the cone, so the angle is no longer, so the phi is not from 0 to, it's not 0 to tangent inverse here. So it's actually from tangent inverse all the way to pi over 2. So we should fix this by taking the integration limit. This is going to be the lower limit, and then the upper limit should be pi over 2. So this is tangent inverse 1/8. This is 90 degree because of this phi represent angle from the z-axis rotate all the way. This is pi. So we go from here to here. That's the integration limit for phi. If I fix the integration limit for phi, we should fix the whole calculation. Right, so we can calculate this, the 5 cubed over 3 is integration for 0, which doesn't change. The e theta will still be 0 to 2 pi, that will still be 2 pi. The one that we should adjust or correct my mistake is integration limit for phi was wrong because the integration region is above the xy plane but outside the cone. So it should be upper limit at pi over 2, but cosine pi over 2 is actually 0. So this is all we need is the cosine of the angle, cosine of the arctan tangent 1/8. So this will be the direct calculation without doing all those subtraction thing that I did. Let's fix it. If we don't do it this way, we get rid of that one minus, and that's all we need. So okay. It's the same number. This is a direct calculation. You can, like, put in the calculation, you can see that was 0. This is d theta. Over here is d phi, the angle. So when I was reading the question, I think I take for granted that we were calculating inside the code. Since all the example that we did on the paper and on the textbook was within the code, so I overlooked reading the question better. This is the first question on 13.7 is not even a super difficult question. It's me that was not paying attention. All right, let's move on to the second example. I'm trying to explain the process of trying to figure out what's the proper way to set it up. When you read the question does not have a lot of information, or some of the information are not together in the integration notation. So we're trying to find a way to identify what do we have to do to build the whole calculation up. Right? But if you're comfortable reading the solution I posted, it would be better because then all the question had solution in that file. But some of us do not feel like that's easy to understand when the question is already finished. It's different than working on your version of the question. All right, for problem 2, we're integrating z. The E is the solid bounded by the cylinder y squared plus z squared equal to 81, and the plane x equal to 0, y equal to 9x, and z equal to 0. So this one is not a spherical coordinate. You can read the question and realize this is a cylinder. So because we have a cylindrical integration region, we were supposed to do cylindrical coordinate system. However, it's not x squared plus y squared that was in the question. So your spherical coordinate has to be the y and z. So as you try to change your variable, you gotta pay attention to how it's being adjusted, which will affect how you integrate and you calculate. Right, so start from here, we realize we would better have the cylindrical coordinate for y and z. So we would set y equal to r cosine theta and z equal to r sine theta. Okay, so that's just, so then there is a 2 variable already, r and theta. the other variable are not gonna be z, so we're not following exactly how the cylindrical coordinate was set up in the textbook. We did I equal to r cosine theta, y equal to r sine theta, and z equal to z. However, in this question, you have to be flexible and realize that the one that is cylindrical relation is between y and z. X is not in there. You're gonna keep your x variable, x still equal to x, and then have r theta for y and z. So y and z will be replaced, x will stay. So have that part, and therefore, try to identify the integration region. So we would have this integration of, that was our integration question, right? So you're gonna have an integration of z, and then we have the z changed to this. That's because our integration region. So then we decided to do a cylindrical integration, and that's kind of dictate how we go forward. We are not going to integration z because z was replaced, so you're going to integrate r sine theta. This is indicated by that z, but also you still have that dv to work on. Since we're doing this spherical cylindrical coordinate, we have r dr d theta. So because the r cosine theta sine theta, we have r dr d theta being part of the dv. But we did not replace the x, so we still have the dx. I'm not so sure about the integration order, but right now, for now, we write dx, and then there's r, and there's a dr, and there's d theta. Let's see if that works out. Okay. So this is so far the integration function and the integration variable. We have dx, dr, d theta, and then we have to integrate. Look at the integration region to identify what will be a appropriate integration order for integration limit. So I'm trying to draw what's going on. Okay, so y squared plus c squared equal to 81 is a cylinder inside the yz plane. So here is x, there's a y, and there's a z. So you see a cylinder in the yz plane. I guess I'll draw it like this. So it's a cylinder this way. Because there's no x-axis, so it should be parallel to the x-axis cylinder. Try to draw, hope it looks like a cylinder. Right, that's the surface, that's one surface. And then the plane x equal to 0 represents the yz plane. And then the y equal to 9x is inside, it's a line inside the xy plane, which will represent a line like this. Draw a line like this, but at the surface, it will be a surface like this way. Okay, so your the surface, this is the plane, y equal to 9x is plane. This plane gonna intersect the cylinder. Well, the intersection probably gonna look like this. Okay, so when the cylinder cuts through this, the plane cuts through the cylinder, you can have a kind of a, it's at an angle, so it should be an elliptical intersection. And then solid bounded by the cylinder, this plane, and then x equal to 0 plane, which will be the yz plane, and then v equal to 0. So in the yz plane, there's also an intersection. The intersection look like this, and then it gets worse and worse. Maybe I should remove some of this. So you can see the intersection. Try to draw the intersecting this way, and then there's the intersection this way, and there's this line. It's this side from the cylinder. So this part is from the cylinder. Okay, and then this part is from the plane. Try to imagine, you visualize what's going on. The other edge will be, of course, in the plane represented by x equal to 0. And then lastly, we have z equal to 0, which will be z equal to 0 is the bottom part, like this part. Okay, so we're trying to form a kind of like a pyramid, but now on one side is a curve, this side. So we can kind of see on the side how the boundary is up. So All right, I would prefer following the cylinder for the x value. So it looks like the setup for the x in the middle is fine. The x value going through this, which will be the upper bound for the x value. We have to identify what's in the plane. If this is a plane. This plane belongs to y equal to 9x. We solve the x from it. X equal to y over 9. Okay, so for the x value, the lower boundary is x equal to 0, y equal to 9x is to provide the lower bound and upper bound for the x value. So 0 and then y over 9 will be the upper bound for the x value. That's why I'm solving the x and that x. Find the x value from these two equations. So lower bound for the x. Next thing is we want to identify the boundary value. Upper boundary for r and theta. So how do we know it? This is what's telling us. You can see it's bounded in the. Is there another half? Other side. It's bounded by x equal to 0, z equal to 0 in the first octant. All right, if it's in the first octant, then we have only a quarter of the whole. A quarter of the whole circle. So R is going to be between, there was an 81, so the upper boundary for the R is 9. So for the R, upper boundary is 9, lower boundary is 0. So radius will, think about this as a quarter of a circle in the YZ plane. That's our circle. Here says first octant, so 0 to 9. For theta, also it's going to be 0 to pi over 2, 0 to 90 degrees between the quarter circle. So now we have r and theta based on the equation of the cylinder and also its first octant. Now we have all the integration limits set up. We can look at integration for all three variables. Let's see. It's not too messy. My tendency to write on top of things, kind of mess things up. That's the calculation part. That's first integration. The x, our integration function has r and r, so you have to multiply the r. But it's integration of r squared sine theta. But when you're integrating that, you realize that has nothing to do with x. So we have 0 to pi over 9 dx. When you finish integrating it, it's going to be y over 9. Y over 9. We don't have y. We have r cosine theta, so it should be r cosine theta over 9. Over 9. Scratch that. So it would be r cosine theta over 9. That's after you finish the x. X is done. And then we move on to the next layer of integration. We integration the dr. 0 to 9 dr. Okay. And then of course the theta is independent from the r since it's a multiplication. If it's a summation, we're forced to integrate them part by part. But if it's multiplication, the sine theta cosine theta move out of the integration. Integrating r squared, there's another r, so we have to integrate r cubed. Integration r cubed dr is r to the fourth power over 4. We have to evaluate it at evaluate from 0 to 9. Okay, so then dr would end up giving you 9 to the fourth power over 4. That finished the dr. And that's without the integration for theta. Then the integration for theta is 0 to pi over 2. We have, try to make sure, we have this one that we didn't do, this one we didn't do, and then that one we didn't do. Right, I had r cubed integrated, so we did integration of the rest. So it will be bring the 1 over 9 to the outside. It will be sine theta cosine theta, d theta. Okay. So this we can do a substitution method because the root of sine equal to cosine. You can see that is sine theta times the sine theta, because derivative of sine theta is cosine theta, so this equal to this. And therefore, if you do a substitution, it will be u du. Integration u du is u squared over 2. So the antiderivative will be sine squared theta over 2, right? Derivative of sine squared theta over 2 would be this. So that answer. So we'll guarantee that that was derivative. This is the antiderivative. Also expect 1/9. Put in the 0 and put in pi over 2. When the angle equal to pi over 2, sine theta equal to 1, sine pi over 2 equal to 1. So that gives us, after finishing the integration of the theta, it's 1/18. Right? 9 times 2 is 18. So that finished everything. That's, I hope. I mean, let's see if this is all set. I think I integrated dx first, and then integrated dr over here on the right, and then I integrated theta left. Right. The answer is 9 to the power 4 over 4 times 1/18. That's the second example. It does have some difficulty as far as trying to adjust a cylindrical coordinate with the change of variable. Over here is the change of variable. And you want to make sure you change everyone. Like you can see, I just forget to change the upper limit there. Integration function has to adjust it. Integration function also adjust it. That was question number 2. If you want to see a better organized solution, you can go through here. I have a set of questions listed here, and compared to that set of questions, that was a solution. So I posted the solution and the question. That was my graphing there. It's not too tidy, but it's a similar example that that's similar to what we did over here. And that was the example number 2. Maybe I should stop doing the calculation. We can just talk about the scenario or how to set it up. Number 3 had a cylindrical coordinate to calculate this function. Function is z, which was similar to the question 2. And what was the integration region? The region is z between 64 and x squared plus y squared. And this is why we felt like it would be okay to do a cylindrical coordinate. And you can see the integration region, z to x squared and y squared is cone. Z equal to 64 is a plane, right? So z is between a cone and a plane. We do have x squared plus y squared in the integration region, which is the reason why cylindrical coordinate will be better for the calculation. Right, maybe this will be our last example. Do more practice questions tomorrow, and we'll stop doing my awful writing of the calculation. That I'm hoping that by calculating out the detail, you can see how it works out from the beginning. Right, the setup part will be it's a triple integration. And we're doing a cylindrical coordinate, so number 1, you have to know the proper way for the substitution of variable. X squared plus y squared, indicating we will do x equal to r cosine theta. Y equal to r sine theta, and z equal to z. This is our change of variable. The integration function is that was part of variable, so we don't have to switch that variable there. Okay. And also the dv, we rewrite dv as r dz, r dz dr d theta. So this set up the integration part. The rest is the integration limit. This is already a natural boundary for the integration limit, and we had the upper value of 64. The lower value is this, so we have to change. We have to change the variable x squared plus y squared equal to r squared. So that's the integration limit for dz. For r, I believe it's a full circle. this is a cone, so right here we have a cone. Okay, z equal to x squared plus y squared. It's not a cone. It's it's like this paraboloid. It's paraboloid. Lower boundary is a paraboloid, and then upper boundary is equal to 4. So it's volume within this. All right. So then, as you can see, it's a full circle. Drawing this just to say we got a full circle, and therefore the r is from what was the radius of the circle? You pair these two together, z equal to x squared plus y squared, and d equal to 64. We're trying to identify the edge. This edge is going to project onto the xy plane, and that's why I need to know the radius. All right, boundary for the radius. You set up the x squared plus y squared equal to 64. That will be a projection of this edge onto this edge. And you can see it was a radius, the r equal to 8. Radius equal to 8 circle. So r from 0 to 8. It's a full circle, so 0 to 2 pi for d theta. That's how we can set up the integration order and the integration function. Now I think we're ready for calculation. That was everything about setting up problem 3. That should be it for today. Hope it works out. I hope that you can start working on your 13.7 homework. Again, there's already a version of solution online. Also, the textbook could be somewhere you can go back for more example or exercise. And that should be it for today. Thank you.